Hello, in this lecture we will find the radius of the small circle. In the drawing we have a square and we know that AB equals to BC equals to CD equals to AD equals to 8 units. That is to say, the length of one side of square ABCD is actually equal to 8 units, and inside square ABCD we have two circles. The radius of this big circle equals to 2r, and the radius of the small circle equals to r, and we want to find out the radius of this small circle. So first of all, we will define the center of the small circle as point P, and we will define the center of the big circle as point Q. And before I continue, I present to you two new rules. Rule number one states that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So I will read rule number one again. Rule number one states that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So actually, if we have a circle and the center of this circle is here. Let's define the center of the circle as point M, and we have tangent to this circle actually tangent AB is tangent to this circle at point C, and if we have a radius of this circle that is drawn to the point of tangency, that is to say point C is the point of tangency. As you can see, this radius of the circle is drawn to the point of tangency, that is to say is drawn to point C. Therefore this tangent AB is perpendicular to this radius, that is to say this angle equals to 90 degrees. It is a right angle, and this angle also equals to 90 degrees. So whenever you have a radius that is drawn to the point of tangency, in this example the point of tangency is point C, and as you can see from the drawing, this radius is drawn to the point of tangency, is drawn to the point C. Therefore, the tangent AB will be perpendicular to this radius at this point, the point of tangency. So this angle will be a right angle, it equals to 90 degrees, and this angle will be also a right angle. So whenever a radius is drawn to the point of tangency, then the tangent will be perpendicular to this radius, that is to say this angle is 90 degrees and this angle is also 90 degrees. And we also have rule number 2. Rule number 2 says that if from an external point two tangents are drawn to a circle, then the lengths of those tangents equal to each other. Is equal to each other. So actually the meaning of rule number 2 is that if you have a circle and from an external point of this circle, that is to say point P is the external point of this circle, from external point of this circle you draw two tangents to this circle, that is to say we draw this the first tangent, this point, the touching point between the tangent to the circle will be defined as point A, and we will draw also the second tangent to this circle, and we will define the touching point between this tangent to the circle as point B. So if from external point to this circle, that is to say from point P, we will draw two tangents to this circle, that is to say tangent PA and tangent PB, then the lengths of these two tangents are equal to each other, that is to say AP equals to BP. Okay? So actually that is the meaning of rule number 2, that if you have external point and from any external point you draw two tangents to a circle, then the length of those two tangents will be equal to each other. So in this example, AP will be equal to BP. Okay, so that are the two rules. So in the next step we will join together points A and P, these 2 points, by a straight line. And we will draw radius from point P to the touching point between tangent AB and the circle. Actually, we will define the touching point between tangent AB and the small circle as point M, and we will draw radius that is drawn to point M, radius of the small circle. So according to rule number 1, the radius that is drawn to the point of tangency, that is to say to point M, is perpendicular to the tangent, or the tangent is perpendicular to this radius that is drawn to the point of tangency. That is to say this angle equals to 90 degrees. And this angle also equals to 90 degrees. It is a right angle. We will also draw a radius from the center of the circle to the touching point. Let's define this point as E. So, and we will define the touching point between tangent AE to the small circle as point S, and we will join together points P and S. So PS will be also the radius of the small circle. That is to say, it will be small r. So according to rule number 1, we have here tangent AE, and we have this radius that is drawn to the point of tangency, that is actually point S. Therefore the tangent AE is perpendicular to this radius that is drawn to the point of tangency, point S. So this angle is 90 degrees and this angle is also 90 degrees. Okay? So in the next step, actually before that, we have here, we define the touching point between tangent BC to the small circle as point F. So point F is the point of tangency between the tangent BC. So point F is the point of tangency of the tangent BC, and we have this radius that is drawn to the point of tangency, that is to say to point F. Therefore the tangent BC is perpendicular to this radius that is drawn to the point of tangency, that is to say to point F. That is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay? And we also know that all the angles of a square are equal to 90 degrees. They are right angles. Therefore, angle ABC of the square ABCD will be equal to 90 degrees. So in square PF, in square PF MB, we have 3 right angles, and the sum of 3 right angles is 270 degrees because it is 90 times 7. And we know that the sum of the angles in any quadrilateral equals to 360 degrees. Okay, so we have 3 angles that the sum of them is 270 degrees, and we know that the sum of all angles in any triangle, in any quadrilateral, is 360 degrees. Okay, so we have 3 angles that the sum of them is 270 degrees, and the sum of the angles in any quadrilateral equals to 360 degrees. So in order to complete the sum of the angles in our quadrilateral to 360 degrees, the fourth angle must be equal to 90 degrees. Okay, because 90 degrees plus 270 degrees will be equal to 360 degrees. So we found out that this angle is also a right angle. So in quadrilateral PFMB, this small quadrilateral, we have 4 right angles. And any quadrilateral with 4 right angles is defined at least as rectangle. Okay? So quadrilateral PFMB, this quadrilateral, is at least rectangle. And we know that the opposite sides of any rectangle are equal to each other. So PF equals to MB, but PF equals to R. This is the radius of the small circle, so MB will be also equal to R. And likewise, side PM of rectangle PFMB must be equal to the opposite side FB. But PM equals to R, so FB will be also equal to R. Okay, so actually we found out that quadrilateral PFMB is actually not just a rectangle, but it is a square with all of its sides that are equal to each other, and with 4 angles that are equal to 90 degrees. So PFMB is a square. Okay, and FB equals to R. Okay, so in the next step we will prove that those 2 right triangles can go into each other. So we will focus on the right triangle AMP, the right triangle AMP, and the right triangle APS. So I will repeat again. We will prove that the right triangle AMP is congruent to the right triangle APS. Actually, AM equals to AS, AM equals to AS, according to rule number 2. According to rule number 2, AM equals to AS. Why? Because we have the external point A. Point A is external to the small circle, is external point to the relation to the small circle, and from point S we have two tangents to the small circle, tangent AM and tangent AS. And according to rule number 2, if you draw from external point of a circle two tangents to a circle, to that circle, then the length of those two tangents will be equal to each other. That is to say, AM equals to AS according to rule number 2. Okay, again, AM equals to AS according to rule number 2. Actually, MP equals to SP, MP equals to SP, and both those two segment lines are the radiuses of the small circle, so MP equals to SP equals to the radius of the small circle. Any line segment that exits from the center of the circle and touches the circle, it is defined as the radius of the circle, so PM is the radius of the circle, and PS, it is also the radius of the circle. And we have AP, that is a common side, it belongs to both triangles. So AP equals to AP, it's a common side. That belongs, side AP belongs to both right triangles, to triangle APM and to the right triangle APS. Okay? So actually AP equals to AP is a common side, and we actually proved that three sides of the right triangle AMP are correspondingly equal to three sides of triangle ASP. Therefore, we actually proved that the right triangle AMPs can go into the right triangle APS according to side rule. So I will write it down. The right triangle AMP is congruent. This is the sign of congruent. The right triangle AMP is congruent to the right triangle APS according to side rule. According to side rule. As you can see here, we have three sides. 3 sides of triangle AMP that correspond equal to 3 sides of triangle APS. Therefore, those two triangles can go into each other according to side rule. Okay, so when you have 3 sides of one triangle that are corresponding equal to 3 sides of the other triangle, then those two triangles can go into each other according to side rule. Okay, so those two triangles can go into each other according to side rule. Okay, so from the fact that those two triangles can go into each other, we will conclude that those two angles are equal to each other. Those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. That is to say, angle MAP equals to angle PAS. Okay, angle MAP equals to angle PAS. Again, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other. Therefore, those two corresponding angles will be equal to each other. And if we define angle MAP as alpha, then angle PAS will be also equal to alpha because of the fact that those two angles are equal to each other. So we actually found out that angle MAP equals to angle PAS, and both angles are equal to alpha according to our definition. Okay? So in the next step we will do another construction. We will join together points A and Q by a straight line. And we will join together points Q. First of all, we will define the touching point between the tangent AE to the big circle as point L. Again, the touching point between tangent AE to the big circle will be defined as point L. And then we will join together points Q and L by a straight line. So actually QL, it is a line segment that exits from the center of the circle and touches the circle at point N. Therefore, it is defined as the radius of the big circle is equals to 2r. And we also know, according to rule number 1, the tangent AE is perpendicular to this radius that is drawn to the point of tangency, that is to say, the radius, this radius is drawn to the point of tangency, that is to say point L. Therefore, the tangent AE is perpendicular to this radius, that is to say, this angle equals to 90 degrees, and this angle also equal to 90 degrees. And the same thing is true about this radius. We will define the touching point between tangent AD and the big circle as point G. So the point of tangency is point G. AD is tangent to the big circle as point G. So point G is the point of tangency. So we have this radius of the big circle that is drawn to the point of tangency, that is to say, it is drawn to point G. Therefore, according to rule number 1, that this tangent to this circle is perpendicular to this radius that is drawn to point G, that is actually the point of tangency. So the tangent AD is perpendicular to this radius, that is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay? And we will define the touching point between the tangent DC to the big circle as point H. And then we will join together points Q and H by a straight line. Again, according to rule number 1, so QH is the radius of the big circle. The radius of this big circle is drawn to the point of tangency, that is to say, to point H. Therefore, the tangent DC is perpendicular to this radius that is drawn to the point of tangency. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees. And we also know that all the angles of a square are equal to 90 degrees. That is to say, angle ADC equals to 90 degrees. That is one angle out of 4 angles of the square ABCD. So it equals to 90 degrees. So actually, in quadrilateral DHGQ, in quadrilateral DHGQ, we have 3 angles that are right angles. So the sum of 3 right angles is 270 degrees. And we know that the sum of the angles in any quadrilateral, and especially in quadrilateral DHGQ, equals to 360 degrees. So we have three angles that the sum of them is equal to 270 degrees. And in order to complete the sum of the angles in quadrilateral DHGQ to 360 degrees, the fourth angle must be equal to 90 degrees. I will write it down. In quadrilateral DHGQ, we have three angles that the sum of them is 270 degrees. And we know that the sum of the angles in any quadrilateral is equal to 360 degrees. So here, in order to complete the sum of four angles in quadrilateral DHGQ to 360 degrees, the side of the fourth angle must be equal to 90 degrees. In order to complete the sum of the four angles to 360 degrees, because of the fact that 270 degrees plus 90 degrees equals to 360 degrees. So in order to complete the sum of the angles in quadrilateral DHGQ to 360 degrees, this fourth angle must be equal to 90 degrees. Again, we know that any quadrilateral that has four right angles, as this quadrilateral, is at least rectangle. So quadrilateral DHGQ is at least rectangle. Okay? And we know that the opposite sides of any rectangle are equal to each other. So the opposite sides of rectangle DHGQ are equal to each other. So AQ equals to the opposite side to DG. AQ equals to DG. But we know that AQ equals to 2R, so DG will be also equal to 2R because of the fact that those two sides are equal to each other. And we also know that side GQ of rectangle DHGQ is equal to the opposite side DH, because opposite sides of rectangles are equal to each other. So GQ equals to DH. GQ equals to DH, because in any rectangle the opposite sides are equal to each other. But we know that GQ equals to 2R and GQ equals to DH, so DH must be also equal to 2R because of the fact that those two sides are equal to each other. So we actually found out that the shape DHGQ is not only, or it is not a rectangle, but it is a square, because it has four angles that each of them is 90 degrees, four right angles, and it has also four sides that are equal to each other, that is to say they are equal to 2R. Okay, so quadrilateral DHGQ is a square with side DG that equals to 2R. Okay, and here actually we know that AD equals to 8 units and DG equals to 2R. So the size of GA is actually AD minus DG. Again, the size of GA equals to DA minus DG. That is to say, it equals to DA, that is 8 units, minus DG, that is 2R. That is to say, GD equals to 8 minus 2R. And likewise, also here, the size of okay, we already found out that this side equals to R, and the size of actually, if we focus on this triangle, the right triangle AMP, the size of AM will be equal to AB minus MB. Again, the size of AM, if the size of AM equals to AB minus MB. That is to say, the size of AM equals to AB, that is 8 units, minus MB, that is R. So we found out that the size of AM equals to 8 minus R, and the size of GA is actually 8 minus 2R. Okay? So in the next step, we will prove that those two right triangles can go into each other. That is to say that triangle ALQ is congruent to triangle AGQ. Okay? We prove the triangle ALQ, this right triangle, is congruent to the right triangle AGQ. Okay? Again, we prove the triangle ALQ congruent to triangle AHQ. First of all, we know that AL equals to AG, AL equals to AG according to rule number 2. Okay, AL equals to AG according to rule number 2, because from external point A is external to the big circle, and from point A we have two tangents to the big circle, tangent AL and tangent AQ. And according to rule number 2, if from external point of a circle you draw two tangents to that circle, then the length of those two tangents are equal to each other. That is to say, AL equals to AG according to rule number 2. AL equals to AG according to rule number 2. And we also know that QL equals to GQ equals to the radius of the big circle, that is to say to 2R. QL equals to GQ equals to the radius of the big circle, that is actually 2R. I'll repeat again, QL equals to GQ equals both of those two line segments are the radiuses of the big circle, that is to say they are equal to 2R. And we have a common side, AQ is a common side, it belongs to both right triangles. So we write down that AQ equals to AQ. AQ equals to AQ. It's a common side that belongs to both triangles. Okay? Again, AQ equals to AQ. It's a common side that belongs to both triangles. Okay, AQ equals to AQ as a common side that belongs to both triangles. So we actually proved that the three sides of the right triangle ALQ are correspondingly equal to the three sides of the right triangle AGQ. Therefore, we proved that triangle ALQ is congruent to triangle AGQ according to side rule. So I write it down. Triangle ALQ is congruent. This is the sign of congruent to triangle AGQ according to side rule. Okay, so actually from the fact that those two right triangles congruent to each other, we will conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So those two angles are equal to each other, that is to say angle LAQ is equal to angle GAQ. Again, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore those two corresponding angles will be equal to each other. And if we define angle LAQ as beta, then angle GAQ will be also equal to beta. Okay, so we actually found out that angle LAQ equals to angle GAQ equals to beta according to our definition. But we know that angle DAB is one of four angles, one out of four angles of square ABCD. And we know that all four angles of a square are equal to 90 degrees. They are all equal to 90 degrees, that is to say angle DAB equals to 90 degrees. Angle DAB equals to 90 degrees because it is one out of four angles of square ABCD. Angle DAB equals to 90 degrees as one angle of a square that equals to 90 degrees. But actually angle BAD consists of four angles, and the sum of those two angles, it is actually equals to angle DAB that equals to 90 degrees. So we can write down that 2 alpha plus 2 beta equals to 90 degrees. 2 alpha plus 2 beta is actually equals to 90 degrees. That is the size of angle DAB. Okay. This will be question number 1. Equation number 1 states that 2 alpha plus 2 beta equals to 90 degrees. Here we will divide this equality by 2, and we will get that alpha plus beta equals to 90 degrees over 2 is 45 degrees. But if alpha plus beta equals to 45 degrees, then tangents alpha plus beta will be equal to tangents 45 degrees. Okay? Tangents alpha plus beta will be equal to tangents 45 degrees. Okay, so, and we know that tangent 45 degrees equals to 1, so we write here that tangent alpha plus beta equals to 1. But we also have trigonometric identity for tangent alpha plus beta according to the following trigonometric identity. The value of tangent alpha plus beta, it is actually equals to tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. Okay, so actually you can substitute the value of tangent alpha plus beta in equation number 1 by this expression, because this expression equals to tangent alpha plus beta. Okay, so we will do it now. So equation number 1 will become, instead of tangent alpha plus beta, we will write down this expression equals to tangent alpha plus beta equals to tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. Okay, and according to equation number 1, tangent alpha plus beta equals to 1. So we got this equation number 1 that states that the value of tangent alpha plus beta equals to 1. Okay, in the next step we will calculate the values of tangent alpha and tangent beta according to our drawing. As you can see here, this is a right triangle, so in the right triangle AMP, we know that tangent alpha is actually the relationship between the angle that is in front of tangent alpha divided by the side that is near tangent alpha. That is to say, it equals to PM over AM. Okay, so tangent alpha equals actually to PM over AM. But we know that PM equals to R and AM equals to 8 minus R. So in total we got that the value of tangent alpha is actually equals to R minus 8 minus R. So we found out the value of tangent alpha. Tangent alpha equals to R over 8 minus R. In the next step we will find out the value of tangent beta. Here we have a right triangle, and this angle is angle beta. So tangent beta will be equal, if we focus on the right triangle GQA, in the right triangle GQA, tangent beta will be equal to GQ over AG. GQ equals to 2R and AG equals to 8 minus 2R. So in total we got the tangents beta equals to 2R over 8 minus 2R. We repeat again. We found out that tangents beta equals to 2R over 8 minus 2R, and we have already found out that tangents alpha equals to R over 8 minus R. So in the next step we'll substitute tangents alpha and tangents beta in this equation number 1 by the value of tangents alpha and tangents beta that we found in these equalities. So in equation number 1 we have tangents alpha, and tangents alpha, as you can see from this equality, it equals to R over 8 minus R plus tangents beta equals to 2R over 8 minus 2R over 1 minus tangents alpha times tangents beta. Tangents alpha times tangents beta and all equals to 1. So again we substituted tangents alpha and tangents beta in this equation number 1 by the values that we found for tangents alpha and tangents beta, and we got this equation number 1. Actually we have here one equation with one variable that is actually R, that is the radius of the small circle, and it is very simple to solve one equation with one variable. So here we will take a common factor of these two expressions, and we will get that in the denominator we will have 8 minus R times 8 minus 2R and here it will be R times 8 minus 2R plus 2R 8 minus R. So actually this expression is equal to this expression. We just took a common factor for these two expressions and we got this expression. It exactly equals to this expression, and then we have also the denominator that is actually over 1 minus R over 8 minus R times 2R over 8 minus 2R all equals to 1. So in total we got this expression, and we'll substitute 1 by 8 minus r over 8 minus r times 8 minus 2r over 8 minus 2r in order to have a common factor with this expression. Okay, and we'll get that r 8 minus 2r plus 2r times 8 minus r over 8 minus r times 8 minus 2r over again, instead of r we will write down 8 minus r over 8 minus r, that is actually equals to 1, and 8 minus 2r over 8 minus 2r, it is actually also equals to 1. Okay, so actually this expression equals to 1. Okay, so we substituted 1 here in the denominator by this expression that equals to 1. And then we have also this expression that is actually it is actually 1 minus this expression r times r. We have the denominator that is actually 8 minus r times 8 minus 2r here, and in the numerator we have r times 2r that is actually 2r squared, so it will be minus 2r squared. All equals to 1 equals to 1. So here we have 8 minus r times 8 minus 2r, and we have here also 8 minus r times 8 minus 2r. So after we will move this expression to the numerator, it will get cancelled by the denominator, so actually 8 minus r times 8 minus 2r will get cancelled with 8 minus r times 8 minus 2r. So what is left after we cancelled 8 minus 2r? It is actually r times 8 minus r times 8 minus 2r plus 2r times 8 minus r, all divided by 8 minus r times 8 minus 2r minus 2r squared, all equals to 1. So actually this is the expression that is left after we cancelled 8 minus r times 8 minus 2r. Okay, we left only with this expression. Here we will cross multiply this expression, and we will get that r 8 minus r plus 2r, 8 minus r equals to 8 minus r times 8 minus 2r minus 2r squared. So we first multiplied this expression, we got this expression, so here we will open the brackets in both sides of the equation, and we will get that r times 8 is 8r, r times minus 2r is minus 2r squared, plus 2r times 8 is 16r, 2r times minus r is minus 2r squared, and it equals to 8 times 8 is 64, 8 times minus 2r is minus 16r, minus r times 8 is minus 8r, minus r times minus 2r is plus 2r squared, and we have here plus 2r squared minus 2r squared, plus 2r squared minus 2r squared is 0. So plus 2r squared minus 2r squared will get cancelled, it equals to 0. And what is left after we cancelled this expression? Actually we have here 8r plus 16r is 24r, so we have minus 2r squared plus 24r equals to, here we have minus 24r plus 64. So here we will subtract 44r from this equality, and we will get that minus 2r squared equals to minus 48r plus 64. We will add to this equality 2r squared, actually here we add minus 2r squared is minus 4r squared, and here it will be also minus 4r squared. So here we will add minus 4r squared to this equality, and we will get that 4r squared minus 48r plus 64 equals to 0. So we have here a quadratic equation. We will divide this quadratic equation by 4, and we will get that r squared plus r squared minus 12r, 64 over 4 is 16, plus 16 equals to 0. So we actually got this quadratic equation, and we know that the general formula for a quadratic equation is actually ax squared plus bx plus c equals to 0 when a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And the way to solve this quadratic equation, that is to say, to find out the value of x, in order to find out the value of x, we have a special formula that is x equals to minus b plus minus the root of b squared minus 4 times a times c over 2a. Okay, that is the formula for the solution of a quadratic equation when a, b, and c are the coefficients of this quadratic equation and x is the variable that we are looking for. But in our specific quadratic equation, the variable that we are looking for is r. So actually x equals to r, and the value of a is 1, the value of b is minus 12, and the value of c is 16. So we will find out the value of r according to this equality of x. So x equals to r, so we will substitute x by r, so r equals to minus b. b equals to minus 12, so minus b is minus 12. Minus 12 is plus 12, plus minus root of b squared. B squared, it is actually minus 12 square. Minus 12 square is 144. Minus 4 times a is 1, so minus 4 times 1 is minus 4. Minus 4 times c is 16, so minus 4 times 16 is minus 64 over 2 times a is 1, so 2 times 1 is 2. Okay, so 144 minus 64 is 80, so I write it down. We get that the radius equals to 12 plus minus the root of 80 over 2. Okay, so we got this solution to the quadratic equation. We know that 80 is 25 times 4. So we write it down. The radius equals to 12 plus minus the root of 20 times 4 over 2. Okay, so here we know that the root of 4 is 2, so we write it down. We will get that r equals to 12 plus minus 2 times root 20 over 2. 12 over 2 is 6 and 2 over 2 is 1. So we write it down that r equals to 6 plus minus the root of 20, but 20 is 4 times 5. So we write it down. R equals to 6 plus minus the root of 4 times 5. And again, we know that the root of 4 is 2, so we get that R equals to 6 plus minus the root of 4 is 2, 2 times root 5. So here we got two solutions, two roots for r. The first solution is that r equals to 6 plus 2 times root 5, and the second solution is that r equals to 6 minus 2 times root 5. Okay? But we also know that one side of square ABCD equals to 8 units, and the small circle is inside the square. And because of the fact that one side of the square equals to 8 units, the radius of the small circle must be smaller than 8. Okay, I will write it down. AB equals to 8 units. So R must be less than 8 units. But here we got that R equals to 6 plus 2 times root 5, that is actually greater than 8. And the radius of the small circle must be less than 8 units. Therefore, this option that r equals to 6 plus 2 times root 5 is the incorrect answer, and we left only with the answer that r equals to 6 minus 2 times root 5. That is the answer to the question, and in terms of number, r equals to about 1.53 units. Okay. Is approximately 1.53 units. So now I will summarize the lecture. Actually, we wanted to find out the radius of this small circle. Actually, we have square ABCD, and one side of square ABCD equals to 8 units. And we also know that the radius of the big circle equals to 2r, while the radius of the small circle equals to r. Okay, and we want to find out the size of the radius or the value of r. Okay. And actually have rule number 1. Rule number 1 says that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. Okay, so here we have this radius is drawn to the point of tangency, that is to say, is drawn to point C, that is the point of tangency. Therefore, according to rule number 1, this tangent to this circle is perpendicular to this radius at the point of tangency, that is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees. So actually that is the meaning of rule number 1. And we have also rule number 2 that states that if from an external point to tangent are drawn to a circle, then the length of those tangents is equal are equal to each other. Okay, so according to rule number 2, if from an external point two tangents are drawn to a circle, then the lengths of those two tangents are equal to each other. So here I'll explain the meaning of rule number 2. We have point P that is external point in relation to the circle. In relation to this circle, the point P is an external point, and from point A we drew two tangents, tangent PA and tangent PB. So according to rule number 2, the sides of those two angles are equal to each other, that is to say AP equals to BP. Okay? And actually, according to rule number 1, because of the fact that this radius is drawn to the point of tangency, then the tangent AB is perpendicular to this radius at point M. This is to say this angle is 90 degrees and this angle is also 90 degrees. And here it is also the same thing. We have this radius that is drawn to the point of tangency, that is to say to point F. Therefore, this tangent is perpendicular to this radius at this point of tangency. This is to say this angle is 90 degrees and this angle is also 90 degrees. So we have in the small quadrilateral we have three angles that are equal to 270 degrees. So the size of the fourth angle must be equal to 90 degrees in order to complete the sum of the angles in the triangle in order to complete the sum of the angles in the triangle to 360 degrees. Again, the sum of the three right triangles plus the size of the fourth angle must be equal to 360 degrees. So the size of the fourth angle must be equal to 90 degrees in order to get here equality. Okay, so we found out that this angle is also equals to 90 degrees. And so here in quadrilateral PFMB we have four right angles. Therefore quadrilateral PFMB must be equal at least rectangle. And we know that the opposite sides of a rectangle are equal to each other. So because of the fact that this side is R, then this side also must be R. And also we know that PM, the opposite sides of a triangle, are equal to each other. So PM equals to FB, and we know that PM equals to R, so FB also must be equal to R because those two sides are equal to each other. Okay, then we actually focus on those two right triangles, and we prove that those two right triangles can go into each other. So we focus on the right triangle, triangle AMP, on the right triangle, triangle ASP. Okay, we know that AM equals to AS. Again, here AM equals to AS according to rule number 2, because from external point we draw two tangents to the small circle, therefore their lengths are equal to each other, that is to say AM equals to AS. Okay, and we also know that MP equals to SP equals to R. MP equals to SP equals to R. Both those two line segments are the radiuses of the circle, so they are equal to each other. And we also have a common side. AP equals to AP is a common side that belongs to both triangles. So we actually proved that those two right angles congruent to each other according to angle rule. Okay, according to side rule. From the fact that those two triangles congruent to each other, we will conclude that those two angles are equal to each other. According to the rule, the corresponding angles in congruent triangles are equal to each other. Okay, so from and if we define one angle as alpha, then the other angle will be also equal to alpha. So we actually found out that angle MAP equals to angle PAS, and both angles are equal to alpha according to our definition. Okay, so here we have this radius is drawn to the point of tangency, that is to say point G. Therefore the perpendicular AD, the side AD, is perpendicular to this radius at point G, that is to say this angle is 90 degrees and this angle is also 90 degrees. Okay, and this angle is one out of 4 angles of square ABCD, therefore it equals to 90 degrees. And we also have this radius that is drawn to the point of tangency, that is to say point H. Therefore the tangent DC is perpendicular to this radius. This angle, that is to say this angle is 90 degrees and this angle is also 90 degrees. So we have three, and in quadrilateral GQDH we have 3 right angles, then the sum of them is 270 degrees. So the fourth angle must be equal to 90 degrees in order to complete the sum of the angles in quadrilateral GQDA to 360 degrees. This is exactly what we did in this quadrilateral. So this angle is also a right angle, it equals to 90 degrees. So here we have a quadrilateral with 4 right angles, and any quadrilateral that has 4 right angles, it must be at least be a rectangle. So quadrilateral DHGQ is at least rectangle, if not square. And we also have the rule that the opposite sides in a rectangle are equal to each other, and we know that GQ, so according to this rule, GQ equals to DH, because those two opposite sides in this rectangle are equal to each other. But we know that GD equals to 2R, so DA must be also equal to 2R because of the fact that those two sides are equal to each other. And according to the rule that the opposite sides of a rectangle are equal to each other, GD equals to AQ. So if HQ equals to 2R, then GD will be also equal to 2R. Okay, and if GD equals to 2R and DA equals to 8, so actually AQ equals to DA minus GQ, that is to say AQ equals to DA, that is 8 units, minus GD, that is 2R. So in total the value of AG equals to 8 minus 2R. And we can do the same thing here. We know that AB equals to 8 units and MB equals to R. So AM will be equal to 8B minus MB, and AB is 8, MB is R. So AM will be equal to 8 minus R. Okay? So here we know that this angle is a right angle because it is one of the angles of a square that must be a right angle. So this angle equals to 90 degrees. So angle DAB equals to 90 degrees. Okay? But angle DAB consists of 4 angles. So 2 alpha plus 2 beta also equals to 90 degrees. Then we divided the equation number 1 by 2 and we got that alpha plus beta equals to 45 degrees. But if alpha plus beta equals to 45 degrees, then tangent alpha plus beta will be equal to tangent 45 degrees. And we know that tangent 45 degrees equals to 1. And tangent alpha plus beta equals to 1. Okay, so we have a trigonometric identity for tangent alpha plus beta. Tangent alpha plus beta equals to this expression. So we can substitute tangent alpha plus beta in this equality by this expression. So we did it and we got this equation number 1. And then we calculated the value of tangent alpha. Here tangent alpha equals to PM over AM, but we know that PM equals to R and AM equals to 8 minus R, so in total tangent alpha equals to R over 8 minus R. And if we focus on triangle AGQ, then tangent beta will be equal to GQ minus AQ. And we know that GQ equals to 2R and AQ equals to 8 minus 2R. Okay, so in total, tangent beta equals to 2R over 8 minus R. It's all clear. Tangent beta equals to 2R over 8 minus 2R. So actually, we substituted tangent alpha and tangent beta in this equation number 1 by the values that we got for tangent alpha plus beta, and we got this equation number 1. It is one equation with one variable. We solved this equation and we got 2 answers. And the first answer, it is actually R equals to 6 plus 2 times root 5. And the one side of square ABCD equals to 8 units, and the small circle is inside the square, so the radius of the small circle must be less than 8 units. That is the side of one side of the square. So this answer that R equals to more than 8 units is incorrect, because R must be less than 10 units, so this answer is incorrect answer. So we left only with this answer, that the radius of the small circle equals to 6 minus 2 times root 5, or in terms of numbers, it is about 1.53. We'll repeat again. The size of the radius of the small circle equals to 6 minus 2 times root 5, that is about 1.53 units. Okay, that is the answer to the question, that the radius of this small circle equals to 6 minus 2 times root 5 units, or in terms of numbers, it equals to 1.53 units. Okay, thank you very much.